So hello everyone, I think we can start now. So today we're going to talk about graphs, traversals, and trees. So let's start from what is graph. We have to first understand what is graph and then talk how to store it and stuff, right? So a graph is a set of nodes connected by edges, as simple as it is. So for example, like cities connected by roads. For example, to imagine to try it. There are the cities, right? Those are the nodes of the graph. And then there are the edges, the connections. They're connected some way, right? Like there are roads. Right? So we have the nodes, also called as vertices. Right? And then we have the edges. And another like examples of graphs are, for example, like friends, like people connected by friendships, right? Again, here those are like people, and then this is like the connection, like as friendships, right? And then other example, for example, maze cells connected by walkable steps, So most hard, let's say, contest problems turn out to be graph problems in disguise. The vocabulary we have to know is directed versus undirected. So the directed edge is one way, and undirected edge goes both ways. So who follows whom, but then for undirected edges is like mutual friends. Such as, for example, here, this is like undirected, right? It has both things, so we don't even put direction inside. But then if we have like directed, it's something like this. So they have direction, like this is connected to this, this is connected to this, this is connected to this, and so on, so on. We can also have like something like this. So directed versus undirected, right? So other than this, we have weighted versus unweighted. So edges may carry a cost, a road's length, or just exist. So for example, here they are initially unweighted, right? So they don't have any weights, but we can also assign some weights. For example, like they're the cities, right? Let's say they're the cities, and then you have the distance on them. For example, like 10 kilometers, 1 kilometer, 20 kilometers, 30 kilometers, 45 kilometers, 50 kilometers. Like those are the distances, the weights of the edge, right? So degree. Degree is how many edges touch a node. In directed graphs, this splits into an in degree and out degree. So, for example, like degree of this is like 3 if they are like not directed, but if they are directed, like out degree is 2, in degree is 1. Oh no, out degree is 3 because we also have this. Yeah, we don't really have to like go that deep into this like things, but so path, a sequence of edges leading from one node to another. As for example, let's call those edges some way. Let's call it like A, B, C, D, E, F, and then G, right? So the path, let's say they are not directed, right? They are just, you can go from each side to other side to just make it more simple, right? So the path looks like this. For example, from A, so for example, like from A to B, and then from B to D, from D to E, and then from E to F. This is a path. It starts at some point, it ends at some point, and goes through some elements, right? Okay, a cycle is a path that returns to its start. So, for example, if we have a path which is like from A to B, right? And then from B to D, and then from D to C, and then from C to A. This is a cycle, right? Because it just like goes back to the start. So in this case, if it starts from U and goes to V, in this case it starts from U and goes to U, right? So connected. An undirected graph is connected if every node can reach every other. For example, this graph is connected because we can reach from every single node to other single node. Like, it's fully connected. But if we have something over here, let's call it ABCDEFGH. This one is not connected because there is no connection between H and other stuff. Or for example, if we had like something ABCDEFGHIJKJ, they can be connected, but then again, one thing, second thing, right? And then we have a connected component is a maximal connected piece of the graph. So here, this is a connected component. It includes every single connected part and it's a component. Here, this is also a connected component, right? Because it also includes every single possible reachable part, node, and it includes everything, so it's a component. So, notation used everywhere from now on. N is equal to number of nodes, and then M is equal to number of edges. Okay. So now we can imagine what is graph, right? But we have no idea how to actually store it or have it in our code, right? As right now, it's just a picture. You don't even know how to store it. So the way to store it is we have several ways to store graph, right? So the input usually arrives as a list of edges, and we have 3 ways to hold it in memory. So the list of edges, okay, let's see. So the first way is adjacency list, or I don't know how it's even pronounced. It's our default. Let me turn my camera on, I forgot. Or should I? Okay, I won't. Okay, I will. Never mind. Let's see. Yes, I'm visible. Nice. So, the first thing is this one, our default, right? For every node, we store a list of neighbors. So, for example, let's say here we can see like A has neighbors B and C, right? B, C. And then B has neighbors A and D. C has neighbors A and D.
we can't see what you're writing. Oh, wait. Oh, it starts to pop up.
Yeah. And then for D, we have neighbors as B, C, and E, right? B, C, and E. So basically, we are just making a list. Where the recording is on, right? Yes. Yep. So we are making a list of neighbors for every single node. Let's see. So this logic, it takes only O n plus m space, because we have so for why is it O n plus m? Because initially we have O n let's say nodes, right? Like we have the list for every single node. It's still empty, but though, like, even though we have the list, it's O n. And then for every single part of it, we are going to add, for example, from this one, we have 1, 2, 3 edges coming from one thing. So we have the edges over here. We have the edges over here. We have the edges over here. And basically we store every single edge in this list, right? So, and every single edge is being stored from two sides. As for example, from here and from here, right? The same edge over here is also edge coming out from here, and also edge coming out from here. So we store it like that, and we have O m edges in the list. So that's why it's O n plus m amount of space. So and visiting a node's neighbors costs exactly as much as the node has neighbors. So basically, if we want to like visit the neighbors of D, we are going to check the amount of neighbors we have over here, which is basically like B, C, E, 3 neighbors, 3 operations, 3 checking to neighbors. So the way we store stuff, let me show you in the code, is something like this. So we have let's say the amount of nodes, the amount of edges, and then we store a vector of vectors, which is like basically the list of like the vector. One vector is the list of the elements, and then inside of the single part we have another vector, which is the neighbor list. And then after we enter the pairs, like we have the if it gives like let's say, so the nodes are numbered like 1, 2, 3, 4, 5, 6, and so on, right? So if it gives like 2 to 3, so it just gives like 2, 3, right? We have nodes from here to here, and then it gives like, I don't know, 6 to 1, we have nodes from here to here, and so on, right? So after each time, as we receive some u and v, we have to, let's say our vector of vectors is called v. The all graph is stored in v. And then we receive x and y, like one node, second node, right? We have to add like y, v, x, pushback, y. Because we add in a list of x, we add the neighbor y. And then at the same time, we have to do the opposite for the y. So we find y and then we add x, right? So y push back x, right? So and then if we do this like two-sided only if the graph is not directed. If the graph is directed, it only, for example, it gives like 2, 3, so there is a path from 2 to 3, but there's no path from 3 to 2. Like x, y, path from x and y, but then no path from the y to x. So we just don't have this line if it's directed. So this was the default way to store graph. We use this because it's the fastest and the most comfortable, suitable way to use. So other way is adjacency matrix, which is basically a matrix of n on n, because we have n nodes, right? It's a matrix of n sides on n sides to the n on n. And then in this grid, we are going to have ones or zeros, where let's index it 1, 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, and then also add 5. 5. So here, if there is 1, if 0 there is nothing, like if 0 there is nothing, but then if there is 1, it means that there is a path from 1 to 2, right? So it's some, if the V E G equals to 1, there is a path from E to G. So here, if you have this, it means like there is a path from 1 to 2, and also there is a path from 2 to 1, right? So edge lookup is only all 1, right? Because we just ask this and then we get the answer, right? So, but the thing is that it costs all n square memory. We have to store the whole array of connections. And in that case, it may be too much, because if for n equal to 10 power 5, that is 10 billion cells, which does not fit. Like we can't fit 10 memory. No, it's too much. And we only use this matrix if n is small, few thousands at most. And the third part is edge list. Simply the list of A, B pairs. Like just list of the thing. Like we don't build any vector matrix or something. We just store the list. And some algorithms want exactly this form, as for example we'll see in cross-call algorithm later on. So rule of thumb, reach for adjacent list unless you have a specific reason not to. It handles every constraint you'll see this course. This is the default, this is the best. Any questions so far? So we are going to learn the first graph algorithm today, which is going to be BFS, which stands for breadth first serve. So BFS explores a graph in expanding rings. First the start node, then everything at distance 1, then distance 2, and so on. The engine behind it is a queue. First in, first out. So basically, BFS is an algorithm that, let's say we have a graph. And this is our graph. So BFS is basically a way to traverse the graph evenly, getting far from it. Basically, this is distance 0, right? If we start from the node V, this is distance 0. These are the 1 distance, right? Because there's one edge away. And then these are the 2, 2, 2, 2, 2, 2, 2, 3, 3. So with BFS, we are going to visit first the 0 distance thing node, and after we are going to visit all of the 1 distance nodes, and then after we are going to visit the 2 the 2 distance nodes. 1, 1, 1, 1, and then 2, and then 3. And that's why it's called expanding rings, right? Let's see. Little things to internalize. Mark not the moment you include. That's what setting this does here. And marking later when you pop it lets the same node enter the key many times of extra complexity. Because BFS with nodes in order of distance, this you ends up holding the shortest path length. Each node is let's see. So let's talk about the implementation. How do we do this? So let's first have our let's see. So so the way we do it is first we are going to have the list. This one we're going to store our graph, right? So we have n nodes, m edges. We insert everything here, right? And then after we have to insert the edges, right? So we have to do m times, sorry, because we have m edges, right? And then insert the two sides like x and y, and then after that store it in our vector of vectors, right? And as we can see here, n plus 1, if we are doing from indexation from 1, if it's indexed from 1, right? So n plus 1. So we do way x push back y, and then way y push back x. This is the way that we store our graph, right? So we just entered the neighboring list here, m times the amount of edges, and then we add the neighbor of x, y, and then the neighbor of y x, right? So after storing the graph, let's see if we have some question here to practice on, actually. Continue. Let's see, BFS. Whoa. I can't hear you. Sure, I just want to find like a question which is just like very clean implementation of BFS. Yes, we can see like how BFS works here. It's like very nice animated. So, but yes, before we go to this, let's talk about the main principle of it. So we have a queue. As we all know, the queue is a structure where it just represents queue, right? It's like how it's called? FIFO, first input, first out. Yes, first input, first out, right? So what comes first leaves the first, right? So here, example, the logic of working with the BFS is that we have some. Initially, we only have in the queue the starting point, which is V. This is the queue. We have V inside, right? And then after we have V, from every single node, we look for its neighbors. So we look for the neighbors. After we look to every single time we point to some neighbor, as for example, first time this. So as we point to this neighbor, we go to through the neighbors of the V neighbors, and then every single time we check if the node is visited or no. We check that. We will talk about it in like very soon. So after we confirm that the node wasn't visited, we just add the node in a queue. to visit later. And then we add the next neighbor as we see it. And then the next neighbor. And then the next neighbor. And then as we finish at the very beginning, we look to the front, right? That's how we got the V, right? We look to the front, we get the V out, and we continue the process, right? We started looking at the neighbors, and we pushed everything here, and then the next step, as we leave V, as we finish the whole neighbor checking part, we get the next node from the queue. Here it's X, right? We get the next element from the queue, which is X, get it out again, and then do the same neighbor checking part. We go through all of the neighbors, which are these. And then we again check if the node was visited or no. Here in this case, this node was already visited, so we don't add it again because there is no need. We already added, right? And then we have this. So we add B, C, D. Then actually, why am I putting it? Characters 1, 2. It's supposed to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 0, 1, 2, 3. And then after we finish, okay, 4. Sorry, there was 4, but we ignored the 4 because honestly, anyways. So we added the neighbors, and then after that we finished with the 0, and then we start again taking an element from the queue here, and then looking for the neighbors. And then as we look to the neighbors, we see that the 0 is already taken. There is a history of 0 being taken, so we don't touch it again. And then just take the neighbors of X, the neighbors of 1, the neighbors of the element that we just took out. We add it to the queue, 4, 5, 6, and go for the next element and continue doing it. And in this way, every single element is going to be visited on their own, depending on the distance, shortest distance from the starting node. Because it's kind of spreading, right? So we have the start. First, we are going to look for the direct neighbors. It is the first layer. And then after, we are going to continue from the neighbors. This neighbor, this neighbor, this neighbor, this neighbor. Like, they're already in the queue. And then as we look through each neighbor, we are going to see like other layer of neighbors. And we are going to add this, and then as we visit this, we are going to add this, as we visit this, we are going to add this, as we visit this, we are going to add this. Again in the queue. And then after that, we are going to see another layer, and so on, so on, so on. That's why we are getting the elements coming in the layers from the shortest distance to the furthest, to the longest. Here, let's look at the implementation. Illustration. So, adjacent list. There was one element in the queue, right? The starting 0. So, that adjacent list is 5. its neighbors, right? 5, there is a thing, and then 4 and 1, right? So 4, we check if it's visited or not. It's not visited, okay. We add it to the queue. And then there is a 1 over here in the list, again connected to the 0. We add it to the queue. Right? We finish visiting nodes from 0 and then we get out of it. I get rid of it. The current node is the first node coming in the queue. It's 5. The 5 at least is like 0, 6, 9. Current neighbor 0 node is already visited, so we don't visit it again. We move like more. Current neighbor 6. 6 is not visited. We check 6 and then we add it to the queue. Right? And then 9, the next neighbor, it's not visited again, so we add it to the queue. And then we finish with 5 neighbors and then we pop it from the queue. And then we continue. The next node is going to be 4 from the queue, the front of the queue. And the list is 0 and 2, right? 0 is already visited, so we don't do anything with it. And then we add the 2 into the queue. We finished everything with 4. There are no more neighbors. And we pop it from the queue. And then the next element in the queue is 1. The neighbors are 0, 3, 2. And then we can see that what? Current neighbor 0 was already visited. 3 is not visited, so we add it into the queue. Then we look to the other neighbor 2. And then we see that 2 is already visited. It's already marked. And so on, so on. We continue doing it. Let's finish looking at the animation. So the next comes 9. Current neighbor 6 is visited, 5 is visited. We don't do anything. We finish with 9 and we pop it. 2, 1 is visited, 3 is visited, 4 is visited. We don't do anything else. Just pop it. And so on, again. We just already visited everything, so we just pop. We get rid of everything from the queue. So this is how queue works. No, sorry, not queue, BFS. This is how BFS works. We have another video. So yes, Yusaku Guide is very nice resource you can use. Anyways, so let's write the BFS. But I hope to find a problem with BFS first. Let's see. No, too long. Anyways, we will just write the code without any problem. I will tell the problem. So the problem says that we have to find the shortest distance from a given node to any other node. This is the problem. So after we inserted everything, it also gives us the starting point. Right? So we have to return the whole distance from the starting node to any other node. Shortest distance. So the way it works is that here we can see, where is it? Yes, we have dist, which is initially everything -1. So the -1 thing indicates that it's not visited. Here, vector int dist and +1 for -1. Right? So it means not visited yet. As we can know that we start from the distance is 0, right? So we put this start equal to 0, and then what we do is we push the starting point to the queue, and then the whole BFS part comes in. So while queue is not empty, we continue doing it, right? Every single time we take some x, which is the front part of the current node, we fix it, and then we pop it. And after that we have to traverse, go with the loop through the whole neighbor list, right? So what we do is we can use auto. It is convenient way. Oh no, sorry, no, not auto. But for example, int v2. We put this, and then the list, for example, x. So the way this works is that it assigns it's a for going through the list of this, full list, going through the list, and then assigning the things to 2. Basically, it's for int e equals less than x size e plus plus, and then oopsie, yeah, and then here we have here we have 2 equal to weight. This is this. Kind of. So, the screen share is a bit laggy. This is bad. Is it the same in the notes, or it's very small here, so okay. I don't think I can do anything with that right now, especially maybe in the case of having typhoon coming. So maybe that, I don't know. Yeah, that's one. So here, let's see, what did we stop on? Yes, we traverse. We go with the loop through the list of neighbors. Okay. With the list of neighbors, and then we check for every single neighbor if the distance, if the distance 2 is equal -1. In that case, it's not visited yet, right? We add it to the queue. Push 2. Otherwise, if it's not -1, we don't do anything. It's already done. Like, we don't do anything. We don't touch it. And if it's not -1, we push it, and we also update the dist, assigning this to equal dist x plus 1, because here we can see that where is it? Yeah, it's the distance 0, distance 1, distance 2, and this is only like one step, like we move once, right? So it's plus 1 to the distance, right? So as we can see here, we set up the distance of the start equal to 0, push the start to the queue until it's not empty. We get the element from there, we pop the element from there, we go through the like neighbors, and then for each neighbor we check if the distance is -1, so it's not visited. First time we reach we update the v, and we push the thing like to the queue, the new element, to later on check. So to do things to internalize, mark a node the moment you enqueue it. That's what setting dist v does here. Like, we mark it. So marking later when you pop it lets the same node enter the queue many times and wrecks your complexity. If we were to mark the thing as we pop it, it will make it slower. It will ruin the complexity. So because BFS visits nodes in order of distance, this U ends up holding the shortest path length fewest edges from start to U. This is BFS superpower, shortest path in unweighted graphs. So in the case of having like a cycle here, the way it works is that if this is the 0, this is the start, right? 1, 2, 3, 4, 5. So we first see this, we add 2. We see 4, we add 4. So this is 1, 1, right? And then we see 2, we look from 2. This already visited, this is like not visited. We have 3, we add 3. And the distance is 2, and then that's it. And then we visit this one from the queue, and then this one is already visited, and then this one is like, sure, we add 5, visited, anyways. So here we can see that we get the shortest distance from the start. We don't get like 0, 1, 2, 3, 4, no, because we can't go like this, because this one was already visited before. We don't change it. We don't reach that far because we are going with the shortest distance. Here, 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 and that's it. So each node is encounterwise, and each edge examined a constant number of times. So BFS runs O(n plus m). So grids are graphs too. A maze is a graph where every cell is a node connected to its four neighbors. You don't even build adjacent list from RC to RC, blah 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 blah. So let's see, what does this mean. Let's say we have a grid, and this is the coloring thing. So BFS is used for coloring, right? So this is the graph. We have a grid, and then in the grid it says it's either 0 or 1, where 0 is for empty space and 1 is for tree. Let's mark the tree as a star, or like as a, yeah, not a star. So those are trees, those are blockages. And here it's a graph where you can go from every single point, for example here, to its four neighbors. So we don't even have like the list for it, because it's obvious. We just can go from RC to R plus 1, C, R, C plus 1, R plus. No. I lied. Or did I? No. Yes, we can go through this, and then R minus 1, C, and then R, C minus 1. Like for neighbors. And we can change it like just like that, without having to sort it, because we know the logic behind it works, right? And then here, for example, we have to mark every single connected component in this forest. For example, this. No, wait. I'll change the color. For example, this. These. And then let's say this. We have to find these elements, because like in every single element, every single component, we can go from every single node to other node, right? Like here, like it's connected, right? So the way we can do this is run a BFS. We go through the whole grid, and every single time we check if the, let's call it C, the grid, if the EG is not equal to 3. If it's not equal to 3, we check if it was visited or no. We have like color, where we color it. And if it's not visited, it's just -1. If it's -1, if it's not visited, we run a BFS from that node, and we go through the neighbors, spreading around, and we color it with some C. No, not C. Color number equal to 1 first. We color it, and then we +1 to the color number. And then we go again. We see another node that is not colored, and it's not a tree. We do the BFS again. This is the way to for example, do the connected components in a grid with BFS. Is it clear?
Yeah, it's pretty clear.
Good. So also we'll cover DFS, depth first search.
What do you say we go right to the problems? Let's get some problems to solve.
With BFS.
Like with anything.
Uh, yeah, but the thing is that I won't be able to cover BFS if we cover the problem. Okay, so we could cover problem now.
Yeah, that monsters looks like a pretty good one for me. Multi-source BFS.
Multi-source BFS
Yeah,
monsters.
let's take a look at that.
So, you and some monsters are in a labyrinth when. Oh yeah. So yes, I was thinking if I should also cover the let's say multi-start simultaneous BFS, or I don't know how it's called.
Mm. Oh, this one's
So
fun.
we'll cover it. Okay, that sounds nice, and then we'll just cover DFS later on in a lecture, like after or something. I don't know. So it says you and some monsters are in a labyrinth. When taking a step to some direction in a labyrinth, each monster may simultaneously take one as well. Like as you move, other monsters also move. Your goal is to reach one of the boundary squares without ever sharing a square with a monster. Your task is to find out if your goal is possible, and if it is, print a path that you can follow. Your plan has to work in any situation, even if the monsters know your path beforehand. So we assume that monsters move optimal. Basically, we can't choose. Like, okay, yes. Let's see. Let's look to the input. The first input line has two integers n and m. The height, the papa. This is the like the limits of the papa, the grid. And then we have n lines, m characters describing the map. Each character is, if it's a dot, it's a floor, it's empty. If it's this thing is a wall, we can't reach there. Not us, not monsters. A is a start, and then M is a monster. And there is exactly one A in the input, basically one start, right? So we have to print yes if the goal is possible, and no otherwise. If the goal is possible, also print an example of the valid path, blah, blah, blah. And the path looks like the UL, right, which is basically like down, up, left, right.
Mm.
And that's it. So let's look to the example. Here we have like this labyrinth, and we have to reach either this point or this point, like on the edge, to to escape, right? So again, so here, um, we can see this is the starting point, right? So as we, for example, move over here, the monster is going to like move here and here and here, right? Get closer. Move over here, they're going to move from here to here to here. So if we move, for example, here, they would come here, here, and then we'll just be dead. Like they will trap us after, right? So we have to find the correct way to escape the labyrinth, avoiding the monsters. So, what is the logic? How do we solve this? Any ideas? Duman can.
We can run multi-source BFS for all the monsters and the player. And with then each grid has the following information is first of all the shortest amount of steps for the player to reach that spot and whether a monster is able to access that spot before the player does. Then we can get a set of all of these blocks to see if the original starting point connects to any of the boundary any of the destinations.
So you were saying that you run like a multi something like BFS with starting point on
Yep.
monsters.
The starting point on monsters, all of the monsters and the player.
Interesting. So my
Look at
idea,
that.
my
Okay.
idea is that you can start a multi simultaneous BFS from the monsters only
Hmm.
first. So you start from the monsters first, and then for each monster, you put every single monster into the queue, right? That's
Yeah.
how the multi BFS is done.
Yeah.
You put the monsters into the queue, all of them at first, and
Hmm.
then after that you maintain dist dist eg, which is basically going to be the for
The shortest
each
distance
node.
from a monster.
Yes, the each for each node the shortest distance from a monster, right?
Yeah. Yeah. Exactly.
And then as we have this, after we run the BFS, we have this. After that, we run another BFS from the A, in which we are going to do just not random, sorry, basic BFS, and not only we check for a condition this, like so, the node is not this, but also
Hmm.
to check if the distance of the player to reach
Reach IJ is smaller than the
is yes smaller, not small and equal, but smaller
smaller than.
than this EG.
Yeah.
In that
That's what I'm
sense,
talking about.
yes, in
Mhm.
that sense, we ensure that there is no possible way for any monster to reach this node, so the player is like free to go. And if there is a way from the A to any of the edges, uh, considering this condition, so there is a way to escape the library. Otherwise, there is no way.
Yep.
Is it clear, Duman?
Do you want to solve it, Duman?
Whoa, sounds great. No, it's not clear. Or 50-50.
No, we can write that. Actually, you can just write that to see if it makes things a little bit clearer.
Yes, okay. Of course, I can just implement it. So, let's go. Let's see.
Yay, let's go.
You wouldn't solve it. After you finish this course, you will solve it.
Yeah. ICPC certificate.
Good, good. So, let's see the input, and then I'm sitting so uncomfortably on my leg.
Where
So,
is sitting?
that's confidential information. My
Okay.
back hurts actually. It's just because it's second class. Anyways, so let's start. We have NM. This is the size of the grid, right? So NM, and then the same. Um, uh-huh. And then we have the thousand size, right, of chars, right. It's like and then after that we go through and we go through. I don't like Visual Studio Code actually. It's different. What is this? Anyways, like witness, and then M we insert, so we check it, so so we have two queues, let's say, so we have to store like int in the queues, right? This is monster, monst, and then one is like normal. My naming is horrible, but anyway. And then we check if, say, eg is equal to a, it's the start, right? So we put norm push eg. Otherwise, if it's, say, equal to m, monster push eg, right? So we have everything on in our queues, right? So we also have to have int dist, right? Which is going to be the distance for dist m is like the distance for the monsters, right? So for the from the very beginning, let me actually just a second. I don't like how this. We'll put this. We'll put this. We'll put this. And we'll put this. And then here we are going to how is it called? So this is a minor trick in terms of you avoid not necessary ifs. I'll show you. And then also for the size of array, I usually do this, which is just like you declare some constant thing and then just put n, so you don't change everything every single time as you want to change the size, right? So we go here and then we put say sorry and then we put say eg equal to wall. We set everything walls. We basically, you know how, like, for example, if you were here and it's 0 and then 1, if we want to go over here, it's -1. If we access -1, it's going to go over the boundary and we're going to be sad. But then you just check, like, with if it's like not over boundary, and if it's not over boundary, blah 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 blah. It's unnecessary ifs. So that's why you just usually can like just start from 1 and then put like boundaries all over the walls, so you don't have to do anything other than just checking if the boundary is there or not. And this thing for the dist, we set everything -1, right? And then here we set the dist m equal 0. So here the first the BFS is going to be about the monsters, right? So while monst is not empty, it's not empty, we get element from it, right? We get the monst top front, and then we also pop.
It's a pair.
Yep. And then we also pop monst pop. Auto here is just a thing that just automatically becomes the type that you're assigning. And then as we got the monster out, like the index of the monster, right? After that, we have to check the neighbors, like up, down, left, right, and stuff, right? So it's basically four ifs, or um, if, for example, we have to check, let's say, not just these four neighbors, but also, like, for example, like vertically, not vertically, horizontal, how's it called, like angles, like this. So
Diagonals.
diagonals, yes. So instead of writing like uh, 8 ifs or something, there is a way of you just have two arrays. Two arrays? No, sorry. One array, where it's like directions, directions, where you have like -1, 1, 0, and then after that you can write two fours, four directions, four directions, and it's going to just get the combination of 9 times, like 0, this, and then you just check inside, like for example, if it's not this one, that's it. So
Very
you
nice
can,
trick.
yeah, you can optimize the code in some way, like to not just copy paste and everything, to not have just a messy, not efficient thing, because copy pasting is very slow. But here we'll just do copy pasting because why not? So let's check first the up part. For example, if the let's not call it like x. Actually, let's just put first, and then also right, and then we are going to check if how is it called, s e g, not g, y is not equal to roll. What was that? Oh, okay. So it's not wall, right? In that sense, we also have to check and this m x y, right, is so we just check if it's -1 or no, right? So we check if it's not -1, we make it. I'll add the directions later on. It's just the body for copying. Equal to this m x m plus 1, right? And then we just add to monst push x and y. So this is the body, and then we just have to add the directions to it, right? Is it true? So here, for example, like +1, right? +1. So to avoid the whole thing like this, you could just do the trick over there that I showed. But then we won't do that because we can. Actually, let's do it. Why not? So for that we have like an array. So in case of let's say 4 directions like this, right? We are going to have like +1, 0, -1, 0, 0, -1, 0, +1, right? 0, +1. So the thing is that Let me think for a second. Basically, the sum of the two sides, like two sides, the change of two sides, has to be one, right? Not zero, not two, not minus two. It has to be one or minus one. So we have let's call it the uh, equal to 0, minus 1, and 1, right? So we have 4, which goes from, no, we have 4, and we use int e, this symbol d, very short, very nice, and again int g, this symbol d, very short, very nice. And here we just check if e plus g equals 1 or e plus g equals minus 1. Right? So, in that sense, why isn't that? I don't understand how Visual Studio works. The code is so bad. Maybe I should add some extensions to avoid this messiness. No. So, we check if it's like 1 or minus 1, and then we just plus e and plus g everywhere. Right? Plus g. Why is it n? What? Plus e plus g plus e plus g and plus e. So this time it was kind of slow, but if you initially started to write this thing, it's going to be very fast because it's only one if, one very simple for which you optimize your speed. Right? So you check if it's not a wall, and then if it's not minus 1, you update the distance and you add it, right? So this is the whole BFS for the monsters. And then for the after, for the after, so as we have the distances for the monsters, like to every single node, we also have to do a BFS from the how it's called, from the start, right? And then also it asks for a path, right? So how can we do the path? Any ideas?
Another BFS on a player.
Yeah, I mean, no.
Yeah.
How can we recreate the path? Like R,
Oh,
R. Any ideas?
it's not that trivial thing.
What?
It's not that trivial.
It's not that
Uh,
trivial.
it's like a look. Wait, let me think.
What? It's a what?
Give me a while. Give me a while.
Oh, okay, okay. Of course.
I don't know how to recreate the path.
So, let's say for every single node over here, we would write we would store the node that it came from, like that we reach. For example, for this node, we reach this node from this node.
Oh, I see. Yeah. Yeah, I
So
got it.
so we write, for example, R here, R, and then here we reach this node from this node, R. We here reach this node from this node, so this is down, right? We reach this node from this node, from like, we reach this node from this node, so we write down here. We reach this node from this node, so we write down R here. And then as we finish the BFS, we just look for the like successful escape cases, and you see this, right? And after that, we start from this node and then start to back recreate the whole path. We have like the answer string, we add this, it's R, right? Then go here, like if it's R, we move to the left, go back. So we see this, it's down, so we add to the answer, and then we go up because it's down, like we came from the here going down, so we go up. Yep. And that's the way that we can recreate the thingy. Let's see. So after that, we also have to write down. Let's call it again char way, and also let's store like string answer. No, answer. So what we do is basically recopy the whole thing from here because we are lazy, right? Yes. So here we have the not monsters, but the how's it called, norm, the normal way, normal. So we copy norm, right? Norm, and then pop norm, right? And then we go to the directions, pop, right? So here we also have to anyways write ifs because
Oh,
yes, but I mean the other way around would be doing something else. Let me think to make it more optimized. So basically, instead of this, we can just write down.
we just reverse the index, right? Like reverse. Uh,
What do you mean by reverse index?
you're trying to keep a track of the directions, right?
Yeah. No. It's not that. Like for example,
Okay.
yeah, but you have to like write. Yeah. I mean, yeah. I mean, okay, makes sense. So
Okay.
instead
Hmm.
of char, you just write uh, it's going to be pair. I was trying to avoid this, but anyways.
Okay.
um, so we store the way in pairs, right? So let's see. Norm once we add this norm, right? So here we go through the things, we check if it's and here we check if it's not a wall, that is correct, right? if it's not a wall, and also if the dist m is less, no, higher than what? Are we also going to store another array storing the distance of the guy? I guess we are. This guy.
This guy.
Yes. And then here we just copy this guy. Eg equals to -1. And then here this guy. Eg equals to 0. Yep. And then as we have the dist guy, we also check dist guy uh dist guy e x plus y plus g. So we check if the guy reaches the node faster than the monster, right? So after that we update the dist guy. Oh, sorry, yes. So here we have to put x, y, and +1 because we haven't updated the thing yet, right? So I guess that's it, right? So we go back here, and then as we also did the BFS for the guy, we also have to check the edges, like this whole thing, if there is some answer. So let's say x ans x equal -1, ans y equal -1. So we have to go for n, right? This is going to be the like this one and this one. We check if this guy e0 if this guy e1 is not equal -1, it means that we found the answer. Ans x equal e, ans y equal -1 and 1. Same way, if we found that this guy over here,
If is the answer to everything.
what?
Yeah, yeah, we have to write a lot of ifs in a lot of situations. Like,
Yes, yes,
yeah,
unfortunately. Um, mhm, right?
yep.
And then for int n here one, then we check if I don't like this. Anyways,
Okay. B
we have to check if
it's
one
N.
e
Yeah.
one e and then n e n e, right?
And I. Yeah.
And after that, we found an answer. So if we check if there is no answer, like ans x is equal -1, we see out no, right, and just return. Otherwise, we have an answer, right? So we have to recreate the answer. So how do we recreate the answer? Did we store the? We didn't store the. Yeah. So for the, how was it called? Way.
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 Way. So way x plus
X
e
plus I. X
y
plus
plus
J, Y
z
plus J, dot
equals
first.
to
Oh yeah. Negative I, negative J.
negative I negative j, basically. Yes, good. And then that's it. Here we do, let's say, um, while ons while how was it initial? Let's see. While ans x ans y is not equal I, while we didn't reach the answer, not the answer, while we didn't reach the start, we keep going, and then every single time we're going to check if way oh my god if way ans x ans y equals to let's say -1 0, right? Is it correct? What's wrong?
Yep. Yep.
Why does it work?
Oh. Oh, you need to wrap it around in a pair. Yeah, make pair.
Yep. So if it's -1 and 0, it means it goes to left. No, wait. -1
It,
is up. So it has to be
it
down,
goes
right?
to oh yeah, it goes down.
So the string of answer was how it's called ans, right? So we add ans plus equal down, and then we also do ans x minus minus, right?
Mhm.
And then we do the same thing for the. Oh my goodness. If I
Actually, there are some certain levels of optimization that yeah, I think there's a better way to write. But no worries, yeah, this is the best way to write. When especially when we're coding fast, it's the most intuitive way to write stuff.
Yeah, I mean, we
Yeah.
can do like array with connected accordions and stuff, but
Yeah, 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 yeah. Yeah, no worries, no worries. Just
yeah, that's what I
go
was
to
trying
it.
to like think about at
Mm,
the beginning. But anyways, we just want to finish the class, right? So,
yep. So let's go.
um, so ans plus if it's right, we have to go left, right?
hmm
Y 什么? Wait, I got confused.
Left, then yeah, it is correct.
Yeah, 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 yeah,
Yeah.
yeah. And then for this one, we just do 0 and -1 equal right, and then y plus
Bro, I would spend half an hour debugging this program if I were the one writing it.
plus out yes counts. Whew.
All right, time for the truth.
Come on. What's up? What is happening? Yep,
Yep.
and then control. Sorry.
hmm
um, I don't, I don't like this. Why doesn't it?
Parse error. Did you, huh? Did you check the inputs?
What again?
Or did you check the inputs? Or is it like some sort of input error?
Mm, let me let me see. I don't know. And
It looks good to me.
I don't know. Let me just copy paste it.
Yeah,
Uh, no one cares, right?
no one cares.
Yes, exactly. It's just like Visual Studio doesn't have like the
So that's why using command line is always better.
Shmo. What's that? Huh?
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 Stack Overflow. Oh yeah, maybe you can declare all of these.
Global, yeah.
Yeah, declare all of these ones on the outside of the main.
Yep,
Yep.
it will work now. Anyways, oh,
No
oopsie.
worries, no worries. We got the idea. I think we
No, no,
got the
no, no, no,
idea.
no, 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 no
You
worries.
want to debug it?
Yes, of course. So let's just print out the. Also, like debugging also is a part of the
Oh,
journey.
it's a part. Yeah, it's part of the game. I know. It's part of the
So
game.
we basically do the we print out everything to make sure everything is good, you know. So first we would print out the monster part, right? So how's it called? What's up?
This dist mon dm dist m.
Wait, I don't get it. Why is it? Oh yeah, anyways. So mons e or without. No, wait. Confusing.
The monster is a pair.
Oh, it's a pair. I forgot. Why is it pair? Oh yeah.
Oh,
Oh
it's a
yeah,
pair of
yeah, yeah,
indices.
yeah, I wanted to this.
Yeah, dist m.
Yeah, let's see. Oh, we also have to remove the thing over here to not let the program go further anymore, or just we just take it from here. Oh.
Okay.
So
Ah, it's a
zero
lot of
zero.
negative ones.
This is bad. Why? So we go and we found the error was somewhere here, right? So we go over here, we look. Actually, one of the differences between oh, wait, sorry, one of the differences between Visual Studio and Visual Studio Code is that in Visual Studio we have very nice debugger, you know.
Oh, that's true.
Oh what? Oh yeah, it never enters. That makes sense.
Ah,
So we put over here, we put, but usually you can't really do the same during the contest. So
I think you can because they
I'm
usually support Visual Studio.
no, they don't. It's only code. No,
No, there is Visual Studio. I think there
really?
is. Yeah.
During the RA there was no Visual Studio. I don't know.
Ah, maybe.
I think they don't have usually. I don't know. Anyways, so we check if there is no wall, right?
Hmm.
And this something something is equal, not equal. Oh, it was supposed to be equal to 1 -1. Ah, yeah, accidentally. And again, here it's fine, I think. So let's check. hmm Zero. Everything is zero. Why is zero?
Bunch of stuff zero.
Because yes, because you have to put this. Happens. It's hard to speak and code at the same time.
Yeah, yeah, yeah. True.
And here too, the same thing happens.
Yep, happens. Natural mistake.
And then let's see. Um,
All right, something to do with the while loop over there.
oh, did
Yeah,
you
it's
open?
probably a bit of a while loop or something.
So the way you can check where is it, you can just like print out some random thing.
Yeah.
So before it gets
And I
clogged.
think you have to end the line for it to print out.
No, not necessarily.
Okay.
Alright, what's up? Come on. Fuck. Alright.
The old error.
Yeah, but I don't get it.
Or it says no errors right now. Try again. Bro.
I don't like this. Compilation successful. What the fuck? Oh, maybe I didn't. Alright. Yes, it reaches this point, right? So here we can tell that the infinite loop is not over here. You just move it down. We check here if it's the same one. And again, it's not here, right? So we go down over here somewhere. Is it over here? And then we check again.
You should use the binary search method as introduced a couple of lectures earlier.
So our problem is here, right? So we never reached. So we did something over here bad, right? Let's check.
Yeah. Let's check.
Well, it's not a way. Um, let's see. Pair make pair -1 0 -1 has to go. Has to go down -1. Oh. Oh, yeah, no, never mind. One. Oh, wait. Shouldn't I? I was supposed to. Yeah, something is wrong here. It's either this or that. Basically, let me
Yeah,
see.
why is it minus minus?
I don't know. That's a
But
good question.
it should be plus plus plus, right?
Yeah, I was just thinking, should it be like plus plus or minus minus, and this one is incorrect. Um, so
Yeah,
our way,
depending on where do you think the direction is?
our way was saying like, it was already inversed, right? So we go over there, and it shows over there. We just go back.
So
Right.
going up is well actually going up is actually
Yeah,
uh
this is
yeah.
correct. This is correct, but then we also, yeah, this is correct. It has to be.
The negative one should be going up because you know it's from top to down.
Hmm.
Like n increases from top to down. But yeah, don't worry about the characters right now. Let's see if we were able to
No, I
recreate the
think it's I,
path.
I think it's correct, but anyways, and
Yeah,
also the path is going to be reversed, so you have to reverse it one way. We also
yeah.
expect that. Work, please. Yeah.
Oh yeah, we need to
R
reverse it.
R.
True. Oh yeah, yeah. Let's go. Let's go.
So
Let's
we
go.
just
Let's
reverse
write.
it. Reverse.
RGGR.
So we're looking here. Interesting.
Cyber cow.
That is a concern.
Bro's canceled on the website.
I don't really remember my. Okay, I remember.
Yay. You never
Well,
save your password?
no. So as we can see, it's not submitted. It's good.
Okay.
I have no idea where it's stored.
Desktop.
Desktop.
Ooh, it's a lot of stuff.
Confidential information. Yes.
Yeah.
And then
Hello.
hello.
Oh,
Hello.
you submit executables directly? Oh, no. Right.
Yeah.
Testing. Brr, brr, brr. Accept. All right, that's an exception. Ah,
What?
no way, bro.
No way.
There's no way.
Something's wrong. What's up? Let's check if it's something to do with some weird stuff or it's actually.
Yeah.
But yeah. No, it's actually wrong.
Hmm.
Why? We should know.
Wishiman. Oh. Oh no. Right.
Yeah, again the same thing. Something is up over here. What's up? Why is your mom?
Can you try to print out if it finds an answer?
Let me just see out.
Oh, it should find an answer.
Look, I'll just see out on X on Y. You know why? Would be very nice. Eight.
Mm.
Like stuff.
I'm stuck somewhere.
So way 8. Way 8. Let's see out way 8. Actually, let's see out.
Wait, eight looks odd because you know it
Wait,
should be
zero,
it should
one,
be two
two,
to three or something,
three.
right?
Wait, 1, 2, 3, 3, 4. It's 8. It's 8. Why is it 8?
Yeah, it should be two or three eight or something.
So it's 8 because let me show you. I have no idea. No, because where are they? Why isn't see how it ran? Anyways, so it's
The only
8
ambiguous.
because this guy equals -1. This guy equals -1. So here it's correct. -1 So something is wrong over here, right? So I don't know why it becomes some 1 and e isn't equal -1 isn't equal -1 e1 m. It's also I guess correct, right? So something is wrong over here. Let's type out on 6. I don't get why is it marking as red, but anyways, doesn't matter. Let's see if it changed anything. Nope, not that. oh. So every single time it changes. Why? Right? Why does it change every single time?
Is it because it recognized the monster as the as a destination?
Yes.
Oh yeah, because your character runs over the monsters. Does it?
No, it should not because we have this, right?
Monster larger than this is a god plus one.
So it should not.
No. Hmm.
This guy here is minus 1 plus 0. So let's check also the. So we know that the answer changes wrongly, right? So let's check the this guy. It's also wrong, but let's check. Like, let's see what does it have.
Yeah, I mean, why would this J?
This guy. So let's check. What do we have? We can see it's minus one, minus
Mm.
one,
Yeah, it's all zeros. That's why.
but it should not be right.
Yeah, it should not be. It should be all. Why were they zeros?
Why are they zeros? Let's see. This guy EG equals minus one. Where else are we changing? We are changing all the way on here, right? Something is just wrong. And the interesting part is that you can, like, it's blocked here. It's minus one. So
Yeah.
right. It's very
Yeah, it
interesting.
should be blocked here.
Where's our kicking part? Where did they put it? This guy, this guy, this guy. Where is it? I can see.
Oh, I think the starting point is marked -1 somehow because there should be a because if you look at the sample, like A hides in there, but there's no turning point
Yeah,
in the
this one
root.
should be.
Yeah, yeah, yeah.
So how is it not? How is not?
Oh, you should set it +1 because is it?
No, no, no. It's just.
Oh yeah, true. It should be. Mm.
Oh, oh well. Oh well. That's why. That's why.
Yeah, because you wrapped around.
No, no, no. This
Is
way.
it?
This way.
No.
This guy equal to 0. I should only put
Ah,
this.
yeah, yeah, true.
Oh
Yeah.
my goodness. Anyways,
Mm.
happens. you know, the
It
last time
happens, it happens.
the last time I wrote like enough code was like very far. You know.
No, 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 bro. I think people are gonna benefit so much from this, bro.
Yes, it's very.
Yeah,
It's a very detailed debugging, fixing and stuff.
debugging tutorial.
Yes, it shows correct. So we just get back our old stuff that we just changed, which means the where is it? This one. Let's remove this and then run it. Opa, opa, yes. And yeah, that's it. And then we go over here and then we try again.
It's
And then if it doesn't work this time, we just say goodbye.
yeah, that's it. No, 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 no. It will work.
It will work, I know.
It will work. And then like your position is actually pretty remarkable.
Oh my goodness.
And at least one accepted. At least some
What?
of them accepted.
Oh, we also.
Yeah.
Why are we? Why are we pasting 7?
Ah, true.
No, why? Where are we? It's part of the debug, but I did.
You just cancel out all the debugs, bro. You find all the C outs and make sure that they don't appear anywhere before the end.
I'll just take code from here. I don't have a mouse. Oh my goodness. Yeah, anyways, so yes, we just put and then we just change this part over here. We just move this up here,
Mm.
right?
Yep.
And then it should work. Hopefully. What? I just pasted the code. Perfect. Mhm. No, look over here, look over here. So actually, during the actual contest, you don't have the examples, right? Like, you don't have the
No,
test
no, I
cases.
had to guess. Yeah.
So yes, it's kind of partial tutorial, right? Then also let's at the same time easily check the time limit thing to make sure if it's time limit or no.
So is that why it's usually better to write code in a way that there's less mistakes?
Yes, so there's
Yeah.
time limit here, so I don't really know. Oh my goodness. We check over here again. Oh my god. So some blah, 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 blah. So we check if it works or no. Blah, like this. Oh, it doesn't work. Oh, it does actually. No. And then we then see out the on six and then on zwei. Anyways, yep. Wait, doesn't work. Yeah. And then we get 8 and 7. So it means line 8, 1, 2, 3, 4, 5, 6, 7, 8, and 7. Right, right. And then after that we are supposed to go higher. Let's try to put the same line over here so we see what happens. Oh my goodness. Actually, it should not take actually like so much time. It should be very easy and fast.
I know, right? But yeah, this problem is so easier said than done.
Opa, 62. It's not 62. No, wait. Stop. Yeah, hopefully for better understanding. Stop. Now run. Stop. So we get 2, 6. So we are dying over here in 2. Opa, no. No, go away. So 6 is over here, right? 2, 6. Why do we die at 2, 6? Why do we die at 2, 6? We also have to maybe print out to see what is our thingy, which is way 2, 6. First, and then also way.
But yo, I'm so sorry, bro. I have to go right now.
Of course, of course, of course.
All right. I'll see you. I'll see you.
Yes, yes, yeah.
Yeah. I think the next couple of lectures you can just start talking about problems and we just solve them. It looks pretty fun.
Mm-hmm.
Like,
So yes.
all right, I'll see you, man. I'll see you in the next
See you.
lecture.
Okay.
All
Bye bye.
right. Thanks, bro.
Of course. Bye bye. So Duman, we are left here. So 2 6 2 6 2 and 6. So here we are here and 0 1 0 1, and it should change, and it's not changing. Why it's not changing? I have no idea. Let's see. 0 1 ounce by plus plus. Why isn't it changing? So in this case, let's have another thing here. Just move over the VFS and just see if also is equal ounce y is equal 6. Opa. Let me just copy paste the whole thing over here. Where is it? Yeah, I lost it. Where's the problem? No, there's no problem. There is no problem. The problem is here, right? So if we just check here. Opa, accidentally. Oh, I see. Okay. Found. So the problem is that we also were doing some not correct things over here, because once we enter we should not go and check other things, because we just ruined everything, right? So here, then yes, exactly. So we just go over there. Where? Here. Can we go back? Submit. This is the file. And then we submit. Oh my goodness. What's up? Wasn't supposed to work. What happened? Is it even the... Oh wait, what? Maybe I didn't save it. Yes. Why does it? Oh well, what? I think I didn't save it. I was supposed to... It was supposed to just print Oh no. Never mind, we also have to print the size. So here it's going to work, but it's not going to fully work because we have another time limit, which I don't know from where it comes. But then we'll see. Yeah, no answer. So maybe it asks for shortest distance, I don't know. Let's see. Print the example of our path, blah blah blah. You can print any path as long as it's like at most. Oh, well, it works. It's supposed to. But then we have another thing, which is well, yeah, we are also printing out check over here, which is not supposed to be here. So we fix this 2, and then I'm so tired. Oh my god. When we get time limit, when we examine time limit. So sadly, it also stacks somewhere, and we'll see where right now, because we can open this thing called Windows Studio and then just run it, and hop, and then put the thing over here, and then wait until it goes somewhere over here. And then we kind of stop. And we look over here, and then we see that this is norm to bad. This guy. Oh yeah, we also have to check. I forgot. We also have to check to make sure that this guy by itself. This guy by itself is new, you know, so we don't overdo the thing. So is equal to -1 also. Here we checked it, but here we forgot. So here in that case, we are going to get the answer correctly right away up. Yes. Here we just copy paste. Here. And then we just go over here and then submit it, and then it's going to pass. Right, wrong answer. What? So this is like the worst example of implementing code. You have to make sure everything works correctly, like write the code in a way that you don't make stupid mistakes. But unfortunately, we could not do that this time. This guy. This guy is here. Let's check the monster. No, distance. So here we can see that the distance is this one. This is fine, right? So it's supposed to be good enough. But it doesn't work. So we go over here. We check over here. Like this. And then up. Nothing up, nothing up, nothing up, nothing up. Something is wrong over here. What's wrong? And then we also oh right, so we also have to check that list m is equal, it's either bigger or equal to list m x plus y plus g to -1, which is like guaranteed that the monster can't reach there. So in that sense, now the whole thing is going to work. Of course, right? So we can also check here. Well, I accidentally pasted the whole thing. Fine. Again, and then we just paste that. Yeah, exactly. Then over here, where is it? Just put this. Oh, accidentally double send, but yeah, accept. So as we can see, this was a combination of BFS with a lot of stuff. During the next class, we're going to talk about DFS. This one was like BFS simultaneous BFS with different dots and stuff, and then like recreation of the path and everything, which was very nice. So yes, and the next class we are going to talk about DFS, and then maybe something else. Oh, we'll see. Yeah. So that's it for this class. Thank you a lot. I'll share the PDF, not PDF. Yeah, I'll share the PDF too in the description of this video, and then also I will share the problem set by the end of this week, so you guys can practice. That's it. Thank you for the class, and see you next week.